Upon further inspection, a mechanical integrity podcast goes beyond the data and dives into the people, challenges, and stories behind reliability and inspection. Whether you're in the field or in the office, this podcast is for you because mechanical integrity isn't about assets, it's about the people who keep them running. You're listening to Episode 3, Secrets Behind HIC-SOHIC, Greg's Background Part 2. The goal is to talk a little bit about your past. I mean, I've heard a lot of new stories here in the last couple weeks. I heard a lot more from, because normally it's always started at Monsanto and kind of that path. I don't know. There were a couple different new pieces that I'd heard. I don't know. It might have just been the fact that I think, well, I learned more about the D&B days too, about you guys catching up and being part of DNV and kind of who the crew was. And it was kind of neat hearing who those people, who was part of the crew, and then seeing where everybody ended up, I mean.
Oh, there were 3 industry burst tests that were done back in the 90s. And like one of them, the oldest one that I remember, was where Exxon took a pressure vessel out of service that was severely HIC damaged, put it in a pit, filled it full of water, did 100% AUT on it, the welds and parent plate, prior to testing. They knew where all the cracks were. And then they put acoustic emission sensors and accelerometers on them to measure movement of the steel. Microstructure, what do you call those? I call them accelerometers. They're really, damn it, I'll think of it in a minute. But anyway, then what we did is pressure tested the vessel all the way to leak.
Oh, strain gauges?
Strain gauges, thank you. Yes, put strain gauges on there too. And we took it up in a ramp fashion that was according to the AE test to get a valid AE test. And then we took it all the way up till it leaked. And it didn't leak until it was like 4.5 to 5 times MAWP. And it leaked at an original fabrication flaw. So all the HIC-SOHIC damage that was in it didn't matter.
It wasn't even a thing.
No, and then about 10 years later, CanMet up in Canada did the same exact thing. And that's written about, covered in the Inspectioneering Journal. It was a 2 or 3 part series by a Dr. John Bowker at CanMet. But they had a vessel that I think they got from Suncor or Petro-Canada or somebody, did the same thing to it with the same kind of results. And so we're all like, man, are we overreacting on this HIC stuff? The HIC-SOHIC stuff.
Yeah.
But I mean, and another couple memorable things that happened at DNV were we had 2 JIPs that were very visible in industry. One was on coke drum cracking, and the other one was on high temperature hydrogen attack. And that was really neat to be part of those projects in that day.
Did you know it was HTHA at that point in time?
Oh, yeah.
Yeah. Okay.
Yeah, we've known it's HTHA since the 40s.
Oh, okay.
That's like, if you ever heard the Nelson curves?
Yeah.
That's named after a former Shell engineer named G.A. Nelson.
Right.
Who started trending. It's really empirical. All they do is create this curve based on observed failures and hydrogen partial pressure and temperature. And then plot the failures on the curve. Yeah.
Yeah. Just a French curve.
Plot the failures on the curve and try to stay 50 degrees below. And so that was all we used up until that time. And then when we did this joint project back then, we started looking at hydrogen diffusivity. And there was a guy named Bob Odette, who is a professor from UC Santa Barbara, who was an expert in that area. And we started going after it more scientifically. But as a person with a background combined in inspection, chemistry, and materials, I arrived at this conclusion, and Garrett used to hate me for challenging him on this, but it was like, wait a minute. if the metallurgists are making the predictions on how susceptible it is, why aren't you guys telling the NDE people where to be doing the inspections on the vessel instead of it just being a random kind of willy-nilly thing? Where are the most susceptible areas? Because the other thing about HTHA, a lot of people don't realize is it's not just not just hydrogen partial pressure and temperature and material, but it could also be exacerbated by secondary and tertiary effects like mechanical stress. If you've got a highly stressed area mechanically that's also got the hydrogen and temperature working on it, that's going to increase the susceptibility there.
Why is that? Because it's pulled apart, so there's more space for hydrogen to diffuse?
It's that yes, basically that's it. And it's also, once it starts, then that can help drive it more as well.
Okay.
And then another aspect, there was one more there. Anyway, there's a lot to that story. I don't want to bore you with all that, but there are a lot of cool things that happened at DNV, and to be part of that. And then the other thing too was DNV was one of the biggest suppliers of automated UT. And we started out with the P-scan back in the 80s, the mid to late 80s, and stayed with the P-scan. But we were doing automated UT early on. And then I had the pleasure of working for a while at CTI, which you probably don't even know about. So I left DNV for 2 years when I was in California and worked as a consultant with John McMillan, who's passed away now, but he was very well known in automated UT, and Rich Roberts. You may have heard of Rich Roberts. I don't know. But anyway, we were doing some really cool shit. Like when we were doing automated UT, I'll give you an example. This could work for HIC-SOHIC. Like on the inside of the tower, there's tray support rings that are welded to the inside of the tower with fillet welds.
Yep.
And there's also downcomers that connect the fluid flowing off of the trays and take it down to the next tray and the next tray and the next tray. And those have fillet welds in them. Well, those were the areas that were typically most susceptible for HIC-SOHIC because of the residual stresses of the welding. And so we got to where back then we didn't have phased array like we have today. And what we did is we would set up like 4 transducers on one scanner. So you'd have 4 angle beam transducers, pitch catch.
Mm-hmm.
One sending, one's receiving, one sending, one receiving. And we'd have them set up 90 degrees to one another so that if the cracking was transverse or parallel, we'd detect it. I don't know if you're familiar with UT, but if you're scanning in this direction and the cracking is this direction, you're not going to find it.
Right.
The cracking has best defined if it's transverse to the incident angle of the UT probe. So with 4 on there, then when we're scanning along and that raster arm's going like this with 4 probes, and you can imagine you got those fillet welds on the inside, we're getting great coverage for cracking, like toe cracking coming out of the fillet welds from HIC-SOHIC. And we actually used to do those on PSA vessels too.
Okay.
Because their bed supports could have cracking if the fillet welds weren't really smooth. In fact, on PSA vessels, they try to avoid welds as much as possible. And back in the day, we used to have manways on PSA vessels. 15 years ago, 20 years ago, they quit putting manways on them to reduce the stress risers. And they just put an oversized top head center nozzle on them so that when you went inside, you could go through there instead of having a separate manway on the sidewalk.
Yeah, because the fatigue would be way too much.
Yeah, it's like eliminate stress risers as much as possible.
And that AUT stuff, that was all new then?
Yeah.
Like the concept of using the 90-degree offset, that wasn't even a thing. So what you guys designed? Did you guys actually design the holder?
No, well, we would give feedback. The company that we worked with most, and there was another big company out back then called AmData that was into it, but the P-skin was manufactured by the Danish Welding Institute. and they were pretty good to work with. And we had our own scanners. We had of course, we had our own system, and we could rig up how many we were going to put in there. But we often collaborate with the Danish Welding Institute and spec out what we wanted, and they'd send us something back. And then most service providers now have gotten to the point that they have machine shops and they can design their own scanners, right? One of the biggest issues, most important things with automated UT is making sure you have good encoders so that you'd have precise locations, because you'd want to know where those probes were at any given millisecond, because they're sharing information between them to create the colored 3D images. So a C-scan is like when you're just you're looking at the UT information flat down. Oh, and I forgot to mention, we'd also have a fifth probe on there, which was a thickness probe that we put right in the middle of the 4 probes.
Oh.
So that way we could pick up blistering too.
Yeah.
And so we could get blistering and cracking simultaneously. And then we would construct those 3-dimensional color images. They've come a long way now, but I mean, we were doing that back in the late 80s. And there was another company called AmData. We're doing the automated UT scanning, and they were doing most of their work up in Alaska. And there was some work beginning to being done with it offshore too, like in the North Sea and like where they had the Piper Alpha master eventually. But I think we were doing a lot of pioneering work, and something that a guy named Peter Blauvelt, who was a corrosion engineer with Shell at the Martinez refinery, did that was so cool, because he had an effluent heat exchanger that was riddled with HIC-SOHIC. And when I was at DNV, he had us do 100% AUT scan of the whole vessel, the heads, the walls. And then he had the color graphic images. So what he'd do is he'd take the drawing and lay the plate out flat, like just change it from being a cylinder to a flat plate.
Right.
And then he could look at the P-scan data for 100% of the vessel. And he came up with a way to grade or categorize the amount of damage in any area. So I think he came up with 4 different grading, like anywhere from where there was no damage to there's X amount of damage to a 4th level of damage. And then he marked it up for cutting that plate up, that heat exchanger up, and he made tensile specimens out of them. So for the different graded areas where the damage was, he ran tensile tests on it to see how much it affected the mechanical properties or the physical properties of the steel, to say, was it a problem or not?
Mm-hmm.
And so that helped him prioritize work once the damage was found. So that work was going on in the same era that those burst tests was going on. And the people who were around then were kind of compiling this data holistically to help them make decisions about stuff that was in HIC-SOHIC service.
Was there a lot of lab work done previously, or was the technology kind of come around to the point where all the DAC sensor, the DAC systems and the sensors and all that stuff, did that come around to the point then finally where all of that lab testing work could be done?
There was lab testing being done then, but it was growing because we were really trying to understand the phenomena well. And what triggered the original lab testing were like the failure of the Lamont, Illinois contactor that killed, I can't remember if it was 17 people or whatever in Chicago back in the 80s,
Mm-hmm.
the late 80s. And that just fueled this even more. But there's a phenomena called sulfide stress cracking,
Mm-hmm.
which goes through wall much quicker than just HIC-SOHIC on its own. And the reason for the sulfide stress cracking are weld hardness zones. So there was a lot of metallurgical lab work being done on taking cutout samples of suspected SSC and then doing Vickers microhardness testing across the thickness of the fracture area to look at when the hardnesses went, like typically you're looking at a Brinell hardness of less than, or Sticker's hardness of less than 200 to be okay. If it was 200 or above, it was too brittle. But then that's where we got into too, understanding the importance of post-weld heat treatment on any welding that was done on this equipment. So, and then we went through a phase of looking at what we call fine line steels, because a lot of the HIC-SOHIC was being initiated by inclusions in the steel. And these were typically like microscopic sulfur voids, or it could be an actual microscopic bubble in the steel, because, with HIC-SOHIC, you've got a corrosion reaction occurring at the surface of the steel that's allowing hydrogen to go through the steel to collect at those sulfur inclusions or voids that might be in the steel. So the industry even started producing this steel called fine line steels. And then we did laboratory testing on, okay, what are we seeing now with the fine line steels? And the last conclusion I remember the industry came to, which they were calling it low carbon, or it was called fine line steel. I'm trying to think of what else it was, but fine line steel. But the conclusion they came to was you have less HIC with the fine line steels, but you have higher propensity for through wall cracking with the fine line steels. So there was a lot of really cool work going on especially in the 90s in this area, anywhere from 1987 through 2000. A lot of really cool work going on.
Thank you for listening to Upon Further Inspection, a mechanical integrity podcast. This episode was co-created by Inspectioneering and Core Solutions. If you enjoyed this episode, please join us next time wherever you listen to your podcasts. Until then, stay safe and stay informed. Our producers are Nick Schmoyer, Jocelyn Christie, and Jeremiah Wooten. This podcast is for informational purposes only and does not constitute legal or professional advice. Listeners should seek their own qualified advisors for guidance.